Welcome to the Cultivating Software Performance in Cloud Computing presentation by Chen and Kingsam Chow. So I'll start with Chen. It's my pleasure to introduce her. She's a research scientist at Intel, develops advanced machine learning workload methods for cloud workload characterization, cloud computing performance. As you can see in her bio, she has multiple master's degrees and PhD in applied mathematics and statistics. With her, Kingsam Chow, he's a 20-year veteran of Intel, but recently moved to Alibaba to explore new opportunities and challenges with playing with data and machine learning. So today they will be talking about sharing their insights on optimizing the performance of software applications in cloud, programming and using machine learning analytics on cloud performance data and data-driven analytics framework for software performance. So with no further ado, let's welcome Lee and King Chow for this presentation. Thank you.
Thank you. Thank you, everybody, for attending this talk. This talk is about cultivating software performance in cloud computing, and Kimson and I are co-presenting this talk. And I would like to describe what the cloud is to you and provide you several different perspectives when we view the cloud and what the challenges are when we try to optimize the cloud efficiency. And Kimson later will describe some related work at cloud service providers. So cloud computing is pretty important nowadays when you are surfing the internet, when you're streaming some video, and when you're trying to shop on the internet. So a lot of those things are powered by the cloud. But what I wanted to talk about today is to provide you a different perspective when we look at the cloud. It's not just about how fast I'm getting the request. It's not just about how much power is used in the data center. It is, in fact, there are a lot of efficiency metrics that we can describe the cloud. And indeed, just to think about the cloud, it is quite complex. The efficiency metrics we can think about in different perspectives are capacity, reliability, scalability, and from the workload perspective, from the hardware, software perspective, and agility perspective. For instance, capacity. What do we mean by capacity? How much resources we can hold in the cloud computing center, and how will they affect our provisioning strategy? Reliability, and usually this is through some monitoring schemes from the cloud computing center. What type of monitoring performance data we can get? Scalability. So how we can take advantage of higher core count products for cloud computing. Workload. There are a lot of softwares running in the cloud. And in fact, there are a mixture of softwares running in the cloud. The workload performance and placement is a key aspect for our cloud efficiency strategies. Software and hardware. So in a cloud data center, we have both the software configuration we need to think about, as well as the hardware configurations. And both types of configurations will definitely influence our cloud computing efficiency. Agility. So this really is talking about how fast we can spawn the VMs and how efficient we can place the VMs so that there is less of the cloud computing issues going on in the cloud computing environment. So all these metrics help us look at the cloud from all different perspectives. So indeed, if we want to improve or optimize our cloud efficiency, we're not just going through one particular directions. we need to have a full picture, and we need to think about how we can jointly optimize the cloud. Now here, I would like to present to you some of the primary cloud components from the hardware side, from the software side, and from the user experience side. So from the hardware side, we have the memory, the CPU, the network, and the storage. From the software side, what applications we're running, what are the cloud layers, which I will describe later. And from the user experience side, how satisfied is the customer, how many requests we can process in a unit time, how fast a request can be processed, how happy the customer is. So indeed, from an analytical mind, we're really looking at, for each of the workload here, we're expressing it in a multivariate functions. And let's not be too scared about this analytical expression. This is just help us to look at this problem from an analytical and mathematical perspective. So a workload can be a function or can be described by these components, the memory, the CPU, the network from the hardware side, and from the software side, and from the performance side. The reason we wanted to express it in this is that we can see that when we change the configurations in the software, when we change the configurations in the hardware, it'll change the performance of the workload. How can we analytically try to identify and provide a quantitative understanding of that? And this is quite important for us to further investigate. So indeed, in order for us to investigate, we need a lot of information, meaning we need a lot of information from all these sources. And this information come from our data, come from the monitoring tools. As the famous rich businessman said, you can manage what you can't measure. Let's get to that in a bit. So from the hardware side, there is the memory. There is memory usage we can measure. There is the CPU utilization we can measure, all the instructions per cycle. Or from the network perspective, we can measure the bytes transmitted, bytes received, and also from the I/O perspective. From the software perspective, we can, if you are running Java, we can get the garbage collection logs. We can also get the information from the software configurations. From the cloud layer, really in the cloud, we are having thousands of virtual machines sitting on a lot of servers. These virtual machines are co-tenants that will be sharing some computing resources. So you can think that they are sometimes fighting for resources, and this fight can negatively impact their individual computing performance. So the virtual machine placement is quite important from the cloud layer perspective. Now, from the performance layer perspective, there is the response time, how fast we can process the request, throughput, which is what's the volume of requests we can process within a unit time. So all these different aspects will provide us a lot of information. In fact, we can also look at it from other perspectives, from the data center perspective, the physical servers, the socket, and the virtual machines. All this type of information is quite diverse. And if we think about it, we are having a lot of data just from all these monitoring tools. And all this type of data will give us the information overload. So what I'm opening up here is just for one single VM, there are already a lot of data that describe how the software is performing. So you can see that we do get a lot of information, and it is exactly what we wanted. But we're also overwhelmed with the richness of the information, because how are we going to do this? If we cannot extract useful insight from them, they're just really taking up the space in our storage. And another thing, besides the amount of information we're receiving from all these different sources, there's also the problem of all this type of data are messy in different ways. So some of the data are really log data files. As we can see, for instance, the garbage collection data, it's a log event that's human readable, but not directly pipeable into a principled data analytical pipeline. Or some of the data are not just text data, but it's text data combined with some units of tables. And that's also not directly pipeable into our analytical pipeline. Now, there are other type of data that is already stored in a simple CSV table format. That's easy to manage. However, they can also come into messy and semi-structured data format that present challenge to our cloud computing analysis. So from a data science perspective, when we look at the data, we think about how useful it is. And a lot of data often were collected from the computers indeed are messy or semi-structured data from the data science usefulness perspective. So there are several ways to define what a messy or semi-structured data sets are. For instance, one of the minor issue, the column headers are values, not variables. So we go from the easier one to more severe ones. Multiple variables are stored in one column, or variables are stored in both rows and columns. Multiple types of observation units are stored in the same table. So really, we don't want to have the units stored in the numerical table. Rather, we wanted to view it as a numerical matrix that some data transformation can be done on it. So, for instance, this is a Linux perf log that describes a workload. As we can see, it is human readable. It's telling us at certain timestamp, there are some cycles, and there have some instructions, and we've recorded the cache misses. But this is not exactly what we're looking for from the tidy data or from the analytical usable perspective. And indeed, this is one big challenge in terms of analyzing cloud performance computing. So therefore, we actually proposed this feedback loop approach to assess the efficiency for cloud computing. So we do start with the measure and monitoring part because we do want to gather all the type of information or as much information as possible from the cloud. We monitor the cloud, and as I mentioned earlier, all the data we have are not all clean, right? It's raw data, it's text data, it's log data. Some have tables, some has text all over the place. So what we wanted to do is we wanted to provide a principled way to process and cleanse the raw data. And this process and cleanse raw data will help us to pipe directly into some analytical pipelines where we could be able to use it for anomaly detection, visualization, or some other practical data analytics or simple machine learning algorithms. And then from the learnings we gathered from the analysis part, we can provide feedback to the cloud, and the cloud may be able to execute some of the suggestions detected from the data, and then we'll loop back to the monitoring, and then we continue to improve our cloud iteratively. So how I see this problem really is the main challenge is the data part, the dirtiness of the data, how we can transform the dirty data into the clean data. Because once we have the clean data, a lot of the techniques are usable. And this is essentially what we're covering here. And the advantage of our approach, indeed, transform all the dirty data into tidy data. As you can see earlier, I showed you that a perf log, it's human readable, but not directly pipeable into an analytical pipeline. However, after data transformation, after the cleansing and processing, we're able to see that this is how we would like to define a tidy data. So for data scientists, a lot of our times are spent into transforming the messy data into tidy data. And of course, the following is trying to devise some modeling and algorithms to extract insights from the data. But without this part here, we cannot proceed. So let me tell you what a tidy data looks like. It's really each row is a sample event or a sample object. In here, because due to the nature of the problem we are dealing with, it's a time series. Each line is logging what happened at this particular time. So we have the timeline here. And each column here is describing what happens at this time. So these are describing the cache misses or the instructions or the CPIs. So with the tidy data, we should be able to navigate through the complexity of the cloud. So earlier when we had the information flow, it's really difficult for us to see the hierarchical relationships in the cloud. But the tidy data will help us understand how the information is piped in a hierarchical order. Moreover, with the tidy data, a lot of the visualization and analytical aspects becomes easy. For instance, this is just a simple plot of, in the end, the outcome of this approach. Earlier, we had the messy data. We may not be able to process it. We may not be able to visualize it. We may not be able to extract useful insight from it. But after all this work done on transforming clean to dirty, transferring dirty to clean data, we're able to do a lot of things. Even a visual inspection could tell us a lot about the cloud. So a lot of the companies, cloud service provider companies, are facing this problem. How we can get all the dirty data and make use of them. And Kim-Sung Chow, my co-presenter here, is going to describe a related work for addressing this challenge.
Thank you, Lee. So the problem I face is summarized in this chart. There's a big elephant in the room, so to speak, and different people working on a problem would like to get a piece of data. Let me illustrate a little bit. Let's say you are a software expert. So you tend to look at the problem is, am I writing the best code possible? So they will get some data about how fast the code is running for this VM on that container, whatever cloud containers or VM you're using. There are also experts in networking. So networking experts say, well, is there a networking problem? So that person will collect some data related to networking, network topology, switches data. They'll get a bunch of data and say, well, let's see if there's a problem. And so on. So you also have a lot of tools that are freely available on the operating system. Let me just pick Linux, for example. You see something similar on Windows as well. So on Linux, you have a lot of tools that come with the system, like some of you might have used VMstat, Top, SAW, a bunch of stuff running on top of System. They collect data about the operating system performance, disk I/O, networking as well. So you got data. So people familiar with that data will take that approach. There are also people building the hardware for servers running in the cloud. So companies like Intel or ARM builders, they will put some tools around to help you to look at the CPU, consumption of the CPU, what resources are being used on the CPU. So you also have a bunch of tools If you're running on Linux, the tool is called perf. So you can easily run perf on Linux and get some statistics about how the CPU is used. So what we're dealing with is we have a lot of people looking at a lot of systems running in the cloud. And all these people have expertise looking at certain domains, right? Networking, CPU, hardware, operating system. And combining all this data, we all try to solve one problem. The problem is, well, we run a bunch of software in a set of data centers. So for me, is a few months ago, while I was looking at this, I got a call from a large internet company called Alibaba. And I said that I would like to work on one problem. Can you get me a chance so I can get data from about 400,000 servers so I can really play the game with touching the elephant? They said, yes, come and try it. So in May, I moved to Alibaba, and I worked in the team called the Alibaba Infrastructure Service. So infrastructure service is the layer of servers below cloud providers. So we are talking about how we set up all the machines, all the basic software to support all the services. So the services could be cloud computing, could be e-commerce. Some of you might have known Alibaba through e-commerce, right? So if you happen to shop online, especially in China, you might have encountered something called Taobao. That is something similar to consumer business. Or you might have encountered something called Tmall. Tmall is somewhat similar to Amazon, so they sell a bunch of stuff. That means in Alibaba, we have a lot of different services running on a lot of different machines. Some of them are running in the cloud, some of them are just running in the data centers. And it is still one kind of cloud computing in the sense that we really don't care whether the app is running in this data center or that server, so far as it gets the job done. So in a summary about what I'm facing with inside Alibaba is we have a lot of servers running. And we want to figure out, are these servers doing the best possible job they are? So let me give you an example about the problem with buildings. Let's say we are running one software application inside Alipay, the payment system of company. And that payment system could be running on 1,000 servers easily. And so let's say we figure out that there's a way to save the performance by just 5%. 5% seems like a small number for a lot for some applications, but within Alibaba, especially you're running some application that run on 1,000 servers, 5% means 50 servers. It's a huge number. 50 servers means about saving of 2 racks in the data center. It's a huge gain. So what we are trying to do here is we want to figure out where we can find the saving. Now, we cannot just go through for each application running in this data center and check, can I save 5% here, can I save 5% there? That would be too much work, just like what Lee described. We really want to collect a lot of data to figure out where we should focus our energy on to get the saving, to get the efficiency running in the data center. By the way, feel free to interrupt me anytime when I walk through these slides. So what we are doing here is, can we get a set of metrics that will be somewhat common across all the applications running in the data center? And can we use these metrics not as the tool to solve the final problem, to give us some idea where the problem is coming from? Where is the opportunity we can improve the software quality in terms of performance running in the data center? So when we started looking at that, at that time I was not with Alibaba, but there's a guy from Alibaba, which is one of the co-authors of this paper. He said that it would be cool if we can collect all this data into some central system so we can study it in a method similar to what we described. So we boil down to what are the common metrics we can do. This is one aspect. This is just one aspect of looking at the elephant. If we start with the resources that are being consumed by the hardware to provide all these cloud services, the first thing we might want to look at is CPU utilization, right? So are you using a lot of CPU? And CPU is one of the costly items in a server. may not be the most costly item depending on how you build up a data centers. Memory could be the most costly items, but in some companies it's the CPU. So if you are spending a lot of money on the CPU, you better make good use of the CPU. Then within the CPU, there are a few things we can think about, like putting your software application running in the servers, right? So naturally we think about, can this CPU give me high capacity? So when we talk about CPU capacity, it's really about whether the CPU can give you a lot of clock ticks. For each clock tick is the minimum unit of opportunity to run certain instructions, right? So, so we can get clock ticks by multiple means. I'm going to go through that in the next slide. So the hardware providers give you a number of clock ticks to play with. And you need to run a large number of applications, right? Something like buy shopping on Amazon. So what do? Well, the applications are fixed. We need to serve these customers with these applications. The hardware, once you buy them, they are fixed, right? You can't really change the CPU until you bring a person to upgrade the CPU, right? So then we are down to what can we do about it? So what we are going to do is, for the same applications we are running, can we improve the efficiency of the software quality by reducing the clock ticks per instruction? So given the same number of clock ticks, given the same applications we are running, can we reduce the number of clock ticks we consume per application? In addition, we can also look at can we reduce the number of instructions given that you're running the same app, right? You can use a different compiler, you can rewrite the code, you can improve the software quality. So there are a lot of things we can do. So based on that, we would like to take that approach and figure out what we can do in data collection. But before we get there, let me describe the situation we are in selecting the data center hardware platforms for the software we're running. So CPU utilization, we talk about that, is we want to make it high so that you are spending the resources you have already purchased. Now, in terms of clocks, this is a little bit interesting here. So for a lot of hardware vendors that sell your CPU or the server's platform, you can get more clocks by buying a higher frequency platform. Companies from like Intel will sell you different SKUs, some at higher frequencies, some at lower frequencies. The higher frequencies will give you more clocks, but they are in general also more expensive and consume a little bit more power. The other way we can do is we buy some hardware that has more cores. So that means you have more operating units inside the CPU, and together they give you more clocks. And it is going to be a tough trade-off to figure out what kind of hardware platform we put in to improve the software efficiency quality. And after you get that, for cycles per instruction is we want to maximize the efficiency of the CPU. So you already have the CPU in the data center. You already have some software you're running in the data center, but there is still some way you can maximize. Believe it or not, there are hardware tunables. So you can change the behavior of the hardware to help your software run better. So for example, you have BIOS settings on the servers. And the BIOS settings are usually shared across all the applications you're running on the server. That means you want to either find the right knobs for all the applications that happen to be running in the server, or you move the applications to the server so that you can find the right knobs. So that is the beauty of having a lot of applications running in a very large center is we actually have a chance to say that, well, can we optimize some settings of the hardware and move the applications so that things are more efficient. So we can do all these three things, but ultimately we still have a large number of software developers inside Alibaba or many companies is, well, they like to make their software run fast. So they can make their software run fast by observing the problem that we show them, and they can improve the code. And that's what I'm going to touch on in the next few slides. So again, before I joined Alibaba, there was a guy called Chen. And he thought about the same line of approach to tackle analysis of large number of systems. Again, we're talking about hundreds of thousands of servers running inside about dozens of data centers. And the apps can be running in any server. We really don't know where the app is running. But we can collect the data to find things out. So yeah, it's easy to say we want to collect the data. But then when you say you're collecting data from about 100,000 servers, then people get worried. Well, what if your collector is broken? It breaks the system, right? So we have to go through some tests to make sure that no matter what happens, the collector cannot break any servers. The business will be going on. And not only that, the collectors cannot disturb the system too much. So these are the challenges we need to deal with. But we still want to collect as much data as possible about the servers. Well, after the data are collected, they are, just like what Lee described, they are usually not in the right form for analysis. So we have the tools that we can transform the data into the right forms, similar to what Lee described in tidy data or some form. So far as there's some form, we can analyze the data. Now is probably a good time to talk about this picture and the two Chinese words. Okay, so this is developed in China. So, let me describe the history of this famous doctor in China. So many thousand years ago, there is I don't know why the screen got changed. Okay, there was a famous doctor. So what he did was that he's trying to find the specific treatment for people's disease. But in order to figure out what people are suffering from, he needs to collect data. So he wants to observe the data from the people, what kind of symptoms they have, just like a doctor you can see, you see in America, right? So they observe, they talk to you, they figure out what is the right treatment for you. So Chen came with the name that, why don't we call this tool bench? So bench is a system, we collect data from hundreds of thousands of servers. We pick up the data, and I'm going to have a picture to describe what kind of things we do. And then we use something like an X-ray machine, so to speak, or looks like a smartphone here. And then we apply some kind of diagnostics to figure out where the problem is. Once we figure out where the problem is, we can solve it either by hardware, like changing some of the knobs, or by the cloud management system, change the way we deploy software applications, or just have people rewrite the code. So what we're talking about here is a diagnostic approach to, one, to figure out if there is anomaly in the data center across a lot of servers. Two is, once we figure out there is anomaly, what can we do to improve the quality? At that point, we are going to have some dashboards. Because a lot of the data here is very sensitive, so I'm not allowed to show any dashboards. But I can show you two pictures. Somehow they got approved. So bear with me. But I can talk a lot more than I show. Okay. So this is how the system works. I believe that a similar method is used by many cloud providers. So essentially, we put some agents on each server. And the way the agents work are going to be slightly different depending on the configuration of servers. For example, for some of the systems we are selling cloud services to the customers, we can go inside the VM. So we stop outside the VM. We won't touch anything inside the VM because those belong to the customers. So for those systems, we study the overall system behavior on the servers. We also run other applications inside containers. And in those cases, most of the applications are owned by Alibaba. So we can access the software, and we can figure out what software is being run there, why is the software being running on that server. And we can even figure out which data center, which rack, and things like that. We have that information. So the agents on different servers will do slightly different things. And we do have an agent within a VM or within a container as needed. Now, there are two big groups of information we collect to help us to figure out the two things I mentioned, anomaly detection, and drill down to what we can do about it. So the thank you. The two pieces of information is, well, we want some high-level statistics about what things are happening. So using the high-level statistics, we want to be able to drill down to, is there a specific application within all the data centers we need to pay attention to? That means the application looks like it's in trouble. Or is there a specific server that looks like it's in trouble? Again, I don't have the dashboard here, but you can use this picture to kind of guess what kind of dashboard we have. So we have, go ahead. Question?
So is Banker an open source tool or is it license-based?
What I'm describing is internally within Alibaba, we do use a fair number of open source tools.
But this one is open source? Or?
This solution is not open source. It's a custom solution within Alibaba. The tools are open source. So you can get some of the tools we use like JStorm, Kafka, you can get it from somewhere else. But how we customize it within Alibaba is internal to our company.
So how this is different from Splunk or New Relic?
All the tools are very similar, right? There are a lot of tools like, I am not familiar with the tools you mentioned, but there are Elk and Spider. There are a lot of tools doing similar things. I'm glad you asked the question. When we consider the tools to use in a large-scale monitoring, the number one thing in our mind is the tool cannot break. Not only it cannot break the software running there. So there are a lot of new technologies. Until they are proven not to break anything, we can put it in the data center. And we try to use, I don't know why the screen keeps popping by itself, but sorry for my glitch. Yeah, so we need to verify the tools do not disturb the software system and then put in, and then we need to verify the data can be transmitted correctly. Some of the data are transmitted to a central storage system, you can think of a system similar to Hadoop for big data processing. Then we identify if a machine is in trouble. For example, if a machine has unusually high CPU utilization. So let's say we encounter that. By the way, we usually encounter that. So there are always high CPU utilization, but it could be something good. Like you have more customers coming to your website, so you have high CPU utilization. That is a good thing. But sometimes we don't know if that is the case or if the software is running in trouble. So to figure out whether it's a good thing or bad thing, we have the ability to zoom into, sorry about this. We have, what's going on? How do I keep on this slide? Don't move. Okay, exit presentation mode, okay. Hey, where's the mouse?
It's on the other screen.
Oh, it's touch screen?
Oh no, it's on the monitor.
I can bring it up. Oh, it's there. Okay, I can see here. Okay. Can you make this as big as possible? I'm pretty sure all of you have great eyesight. You have no problem seeing this chart. So we made up an application running in the cloud to highlight what we can do. Even you cannot see the labels of this chart. It's okay. They are not real application because I cannot show anything that's real. Okay. So earlier I said that when we detect anomaly, we can drill down the system. So once you get the system, it will automatically pop up something based on the selection criteria you have. Let's say you notice that a server doing some e-commerce application looks like it might be in trouble. So we noticed that that problem might show up like 10 o'clock earlier today, but we only found out the problem right now. Can we still see it? Yes, we can still see it because the data will be kept around for a while. So we specify from 10 o'clock to 10:05, something funny might be happening on the server. So specify a window, we click a button, we say, show me what it is doing at that time. So it show up from time 10 o'clock to 10:05, the entire time here, what kind of modules are being executed? Is it doing some kind of e-commerce applications which we expect, or is it doing something else which we don't expect? So by looking at the function names here, well, yeah. So by looking at the function names here, the developer can decide whether it's something that they need to pay attention to. I think that is the last slide. So I'm very pleased that I have the opportunity to look at a lot of real data. Actually, it's too much real data, and we are working on a faster method of anomaly detection. Right? We do have to zoom into specific issues really quickly, but we want to make use of a lot of data. So we do big data analytics and lots of graphs, and still trying to figure out what's the best way to do things. Well, yes.
I have a couple of questions
For Lee?
So you mentioned initial part of the presentation about the tidy stuff,
Tidy data format.
tidy data format. So is any kind of tool is being used to create that format, or?
Yes. So the lucky thing is we're dealing with data generated from the computers. So even though they are in a messy format, their messiness is consistent. So there are some tools such as the log stash tool, which is open source, that can deal with the log files. You just needed to specify what information you want to extract from a sentence, and they will extract that for you.
So basically, there is Logstash, Elasticsearch, and then go from there.
Right, and there are the tools. Python itself can do text processing, and R, if the text file is not so large, R can also do the text processing. Yeah, and I think there are a lot of tools in terms of processing the logs and turn them back into tidy data format.
Okay. And another follow-up question was, you mentioned earlier a lot of dirty data is being produced to the logs. So is there any conscious effort is being put to reduce that dirty data?
The thing is, we wanted to monitor the data from the cloud, right? And we do not want to disturb the performance while we're monitoring the data from the cloud. So whatever the computer dumps the data from the monitoring tools, which has very low overhead, we'll just take that. And then we will process the dirty data at a different platform, not really in the cloud.
But sometimes your dirty data can lose some of the information that you really want from the logs. So how do you consume the data that you really want?
Can you repeat the question? Sometimes.
So you said a lot of dirty data is being there in the logs. So how you are managing the log? Is there any kind of standard logging is being implemented? Like in the logs you want only 50 fields to be there, or maybe 100 fields have to be there, and then you can monitor it.
So for now, this methodology I was described was used in our internal, which is a prototype, cloud lab. We are getting hundreds of gigabytes of data, but not terabytes of data enough. We will move to a different methodology in terms of storing the data and processing the data. So for now, what we're doing is we running our experimental cloud lab and then get the data and then process it elsewhere and then extract information elsewhere. So we actually conduct that feedback loop there in a batch sense. But yeah, I think that in a real cloud computing center, there's definitely the need for doing that. And in fact, the ELK tool, they also support when you can store a lot of log files and then only pull up what's necessary for you to do the analysis.
Yeah, from infrastructure point of view, it's fine. But if you have to really monitor your business transactions, you really need to put what is going into the log, and then you can pull it from there and analyze the field.
So I guess you're talking about you first can identify what the log can provide you, right? So, indeed, some of the so for our purpose, when we're trying to collect as much information as possible, we it just collect that. But yes, you can indeed specify from the assessing performance perspective, you can specify whatever counters I wanted to collect in order to assess that. So that's possible to do. Yeah. Thanks.
I guess here, time, yeah. So I just want to thank you, Lee Chen and King Sum Chow for their great presentation, and thanks for all the questions. So just a reminder, please fill out the survey and leave your comments using the PNSQC mobile app. And I think the lunch is on. So thanks everyone for attending this session. Bye.